Hello, welcome back. So today we are going to be talking about our last of the three corner trends. So if you remember, as a review, when we did our periodic table, the three of the big trends that we looked at were atomic size, so larger in the lower left, atomic mass, heavier in the lower right. And today we are going to look at our third cornerstone trend, which is called electron trends are going to be in red. There's three of them, but they follow the same pattern, so we're going to put them all in red. First one we're going to look at is electron affinity. Electron is a word we know, so we're talking about electrons. Affinity is probably also a word you know. So if you have an affinity for something, if I have an affinity for coffee and tea, I like coffee and tea. So affinity means liking or keeping. So electron affinity is the tendency for atoms to keep their electrons. And this is where our pattern from yesterday is really going to become key. So draw our sketch of a table as we do with all of them. So 7 down, 1 over, 1 over, 2 down. Four, 5, 6, 8. So draw our sketch of a table. This time I do want you to drop the column lines down. So that we can talk about how does the tendency to keep electrons change as we move across a table. Now, as we move across a table, we know that the number of valence electrons changes, and we know that the common ion also changes due to those number of valence electrons. So what I want us to focus on today is the common ion. So in column 1, the common ion, red, was +1. So column 1 tended to gain a +1 charge, +2, +3, +-4, -3, -2, -1, and 0. So those were our common ions. And we know that when you have a positive charge, you have lost electrons. So for example, we looked at hydrogen. When you lose an electron, when you lose a negative particle, you become more positive. You lose something negative about you, you become more positive. So we know that any of these positive charges, so this section of the chart, these are ions that tend to lose electrons. So on the left side, we tend to lose electrons. On the right side, we have negative ions. If you are a negative ion, you have taken on something negative. You have extra electrons. So you tend to gain electrons. So this is review. We're just noting it on this page so that we have the information we need to talk about in one spot. So on the left, we tend to lose electrons. On the right, we tend to gain electrons. Now, if we go back to our pattern for our definition for electron affinity, we're looking at the tendency for atoms to keep their electrons. Well, we're losing electrons on the left. So they're not keeping electrons. This would be a low affinity. They're not tending to keep their electrons, they're tending to give them away. On the right, we're tending to keep the electrons we have because we need those and more. So these would have a higher affinity. So as we look at electron affinity, we can see that it would increase across a row. So we go from the left to the right, we're going to see electron affinity, my hands go backwards, we're going to see electron affinity get higher, get larger. Now, as we go down a column, we're going to see a little bit of a trickier trend. But, oops, I should finish this. So, electron affinity tends to increase across a row because the atoms are closer to reaching a full valence shell. So they being the atoms, tend to keep the electrons they already have. So if you're almost out of valence shell, you're going to keep the electrons you already have. You're also going to try and take more, but that's actually not electron affinity. That's a different term that we'll learn in one more video. But for now, electron affinity is increasing across a row because as we go across a row, our atoms are closer to a full valence shell, so they tend to keep the electrons that they already have. Now, as we go down a column, the number of valence electrons doesn't change. What is changing, however, is the size of an atom. So as we go down a column, we get larger. So if we're looking at the first column, if we're looking at hydrogen, hydrogen has one valence shell. So the valence electron that it is holding on to is right next to its nucleus. As we go farther down the column, let's look at, for example, let's look at rubidium. Rubidium is in column 1, row 5. It has 5 valence rings, or not valence rings. It has 5 electron rings. So that's 3, 4, and last one. Here we go. Rubidium has 5 electron rings. Its valence electron is clear out here in ring 5. I'm not going to draw them because they would look dizzy, but there are 36 other electrons floating around inside those other 4 electron rings. So when we talk about electron affinity, which is the tendency to keep an electron, hydrogen is going to be able to hold on to that valence electron much easier than rubidium. Because if we think of that nucleus as a magnet, and that electron is a paper clip, the paper clip is right next to the magnet. That nucleus is holding on to that electron like they're right next to each other. But when we look at rubidium, so rubidium does have a bigger magnet because it does have a bigger nucleus, but there are 4 walls between that nucleus and that paper clip. So that larger atom is going to have a much harder time holding on to its valence electron. This effect is called the shielding effect. And shielding is when inner electron rings protect or prevent the valence electrons from feeling the full force of the nucleus. So when we have high shielding, those valence electrons are not going to be easy to hold on to. They're going to be easy to pluck off. They're going to be harder to keep. So electron affinity, I dropped my marker, is going to decrease down a column due to increased, my screen, yep, atom size and increased shielding. Basically, that outer electron is so far away, it is harder to keep hold of it. So, what does that mean? Electron affinity. Increase across a row, increase up a column. So electron affinity and the electron trends are going to go in the upper right. And this is why atomic size is an O. Because for all of our trends, all you have to remember is OME, kind of like OMG. But OME, you remember OME, you can remember the extremes for all three of our trends. So OME. Remembering that, we're going to do some practice with all three of our trends. So comparing, let's do beryllium and barium. So comparing beryllium and barium, I'm going to do my sketch because I like my sketch. I'm going to add my trends in the colors that I add them in. I'm going to remember my three corners. O, M, E. And now I'm going to answer my three questions. So first trend, we'll start with the lower left. Here's the clock again. So which has the larger atomic radius? Y. Mass, skip like 3 lines, which has larger atomic mass and Y. Skip like 3 lines. Our new trend, which has larger electron affinity and Y. All right, we're going to do this one together, and then I'm going to leave you one to do on your own. So, which has the larger atomic mass? Well, first, I always said first step is to find these on the table and note where they are. So, beryllium and barium. So, we're in column 2. Beryllium is at the top. Barium is at the bottom. So, we've got beryllium and barium. so which is larger? Well, I just need to look at my extremes. So barium is almost on top of my big circle, so barium is obviously larger. Now, most of the points again are how do I know that? Well, I'd have to go back and think about my rules for trends down a column. And if you remember, as we go down a column, the number of electron rings changes. So beryllium is in row 2. It has 2 rings. Barium is in row 6. It has 6 electron rings. So barium has 6 electron rings, while beryllium only has 2. So you've got to activate your brain to think about the right logic. You've got to think about, okay, what's my trend for size? And what's my logic for size as I go down a column? Remembering that your logic changes based on the pattern. Because if I were looking at size in the context of a row, the number of electron rings doesn't change. So that wouldn't be my logic. I would need to go back and think of my different logic. But next one, so which has the larger atomic mass and why? Beryllium and barium. My M is over here, lower. Barium is lower. So barium has the larger atomic mass. If you remember, atomic mass is always the same logic. So barium has more protons and neutrons than beryllium. And then lastly, my new trend, which has the larger electron affinity. Well, I still use my logic for my extremes. So electron affinity is up and to the right. So they're both equally right, but beryllium is, sorry. Okay, I think I'm good. Beryllium is farther up. So beryllium is going to have the larger electron affinity. Why is that? Well, it actually goes back to what we talked about in number 2. So beryllium only has 2 electron rings. So its valence shell is closer to the nucleus. So beryllium's valence shell is closer to the nucleus. So the shielding effect is lower. And therefore, it is easier to hold onto or to keep its valence electrons. So that's the type of logic that we're looking for. I want you to go ahead and answer one set on your own. So you are going to look at, so it's going to be the same questions, except you're going to do, let's do calcium and zinc. And then same questions, I'll rewrite them, but which has larger atomic radius and why? Which has larger atomic mass and why? And then which has larger electron affinity? And why? So go ahead, answer those 3 questions on your own. Really practice using your logic, and if you need to use your notes, that's fine. But you should be getting quicker at this, and you shouldn't need to look in your notes every single time.